Good morning and welcome to AP Statistics. First, I'm going to go over the homework from yesterday, which was page 385, number 59, which gave you a single prompt about time in motion. It says a time in motion study measures the time required for an assembly line worker to perform a repetitive task. The data shows the time required to bring a part from a bin to a position varies normally, blah, 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 11 seconds mean, deviation 2 seconds. Time required to attach the part to the chassis also follows a normal distribution with a mean of 20 seconds, deviation of 4 seconds. Study finds that the time required for the two steps are independent, and the basic question is what's the mean and the standard deviation of the entire procedure? So including the two-step process. Well, the mean of x plus the mean of y equals the mean of the sum. So you'd add 20 and 11 to find a 31-second procedure. Standard deviations don't add, but if you square them, you find the variance. You can add those and take the square root. So we have the square root of 2 squared plus 4 squared. That would be a 4.4721 second standard deviation. All right, mean and deviation done. Now to find the probability the total time takes under 30 seconds, we want to find the z-score for 30 seconds first. So z equals 30 minus 31 over 4.4721 gives us a z-score of roughly negative 0.22. To find the area contained underneath the z-score of negative 0.22, since it's under 30 seconds, use normal CDF from the lower bound of negative infinity, negative 10,000 or whatever you want to call it, to the upper bound of negative 0.22. It gives you a value, an area under the curve of 0.4129. So there is roughly, and it depends on the formula you use, but 4129 or 4115 depends on the output or whether you use a table versus the calculator. But roughly there's a 41-point-something% chance of the procedure taking less than 30 seconds total. And that was your homework. Now, I said that two things will happen today. The first is we're going to talk about transformation of data, which is the second part of this unit. And the other thing we'll talk about is what happens when you don't have independence and you want to find the standard deviation of these joint events. So first thing is the transformation. Here's basically what it means. If I have, let's say, a relationship where y equals x, that's the parent function of a linear equation. If I want to transform it, I want to change it, I can use this equation, which we've already established in statistics, is basically, again, a linear equation where A is the constant shift and B is the multiple shift. We said, when talking about linear regression and correlation coefficients, back in chapter, I think 3, we talked about the effect of the A and the B on measures of center and spread. We had said that the constant, the A, will affect measures of center, like the mean, the median. It will affect the quartiles, 1 and 3. But it won't affect measures of spread, like the standard deviation or the range or the interquartile range. We said that the multiple shift, in this case the B, the slope in the problem, will have a stretching or compressing effect on the curve, which does change the measure of spread, as well as changing measures of center. So the B value, that shift, affects everything. The A value, that shift, only affects measures of center, like the mean and the median. So when we want to affect a change and then apply that same principle to mean and standard deviation, we have to just understand what it's really saying. For instance, if I have a company and the average salary is, let's say, $60,000, and the standard deviation of this company's salaries is $7,000. That tells me something about the center and the spread of this company's salary distribution. Doesn't tell me, of course, the range unless you apply normal probability rules. For instance, if it's a normally distributed population, then 99.7% of the salaries will fall within 3 standard deviations above or below the mean. So $21,000 from 60 would contain 99.7% of our data, and so on and so forth. But that's not the point for right now. For right now, I want to find out how these will change if we affect a linear transformation on the data. So let us presume that everyone did a great job last year, so everyone's getting a 10% raise. A 10% raise is 10% on top of what you currently earn, so it's really 110% of what you made last year. It's a percent increase. It is a multiple shift. So I'm going to leave this blank for a second, and I'm going to write plus 1.1x. Because there's also going to be a constant increase. Obviously, those who make more money will get a bigger raise because 10% of more money is even more money still. So 10% of $100,000 versus 10% of $50,000 is a difference in the amount that those salaries are stretching. So everyone also will get a base bonus of $2,000. That's a constant. So if we want to find out the new transformed values of the new mean and the new standard deviation of my next year's salary distribution, I can apply the following concept. I know that the mean is affected by the constant shift because it affects measures of center, and also by the multiple shift because it affects everything. So the mean that will be new, so mu sub new, will be affected by both 2,000 plus 1.1 times the mean that was old, last year's mean. And so my new mean is going to be $2,000 plus 1.1 times $60,000. And what's that going to be? Well, 1.1 times 60,000 is 66,000, and 2,000 more is $68,000. The distribution has been multiplied by 1.1, so it's spread out and shifted forward $2,000. So the mean has done the same. The mean that was old has been multiplied by the 1.1, and also we added it $2,000 because it shifted forward. What about the standard deviation? Remember, I said the standard deviation is affected by the B multiple shift. Everything's affected by that. But the constant only affects measures of center, because think of it this way. If this is my previous distribution and everyone gets $2,000 more, did the standard deviation change? Did the average distance from a data point to center change? No. Every data point shifted forward uniformly. The $2,000 has no impact on the standard deviation. So, the standard deviation that is new is absolutely affected by the 1.1 times the old standard deviation. But you will not add the constant to the standard deviation's transformation, as a constant does not affect the standard deviation. So that's 1.1 times 7,000, or 7,700. So our new salary distribution has a center of $68,000 with a standard deviation of $7,700. Remember, the standard deviation is only affected by that multiple shift, by the B value. The A value only affects the mean. The B value also affects the mean, but the A value does not affect the standard deviation. You can see this a little bit more clearly in other examples that we'll get to in time. But for right now, understand that these equations are very important. Here's the essential equation, okay? a new mean, we'll say n, so mu sub n is equal to A plus B mu sub O for old. Again, that's the same thing we just did. The new mean is found by taking the constant shift and the multiple shift times the old value. That's easy. But the standard deviation of the new distribution is equal to B times the standard deviation of the old distribution, and we disregard the constant when figuring out that value. Hopefully that makes sense. The worksheet attached to the announcement is 6.2a, and it obviously covers this content. Sometimes some of the questions make you think a little bit harder about the concepts we've been looking at. I need you to try them, put in your best effort, and of course send it to me by tomorrow morning at 7 a.m. If there are any issues, please feel free to email me, and as always, feel free to join the live Google Meet for any interpersonal direct answers if you have them. All right, if you have any questions, let me know. Otherwise, have a great day, and I will talk to you soon.